Hi, welcome to this video. Today we'll be looking at mathematical induction. Mathematical induction is basically a mathematical technique that we use to prove that a statement or a theorem is true for all natural numbers. So how it works is that you have a theorem and you want to prove that it is true for all natural numbers n, no matter the natural number that is in question. It works in 3 steps. The first step is to check whether the statement is true for n equals 1. So checking whether it is true means checking if the left side equals the right side for the theorem or the formula that you're working with. If the statement is true, then we can move on to the second step. The second step requires us to assume that the statement holds true for n equals k, where k is any natural number. Why do we do this assumption? We make this assumption so that we can move to step 3. For step 3, we then need to check that the statement or the formula is true for n equals k plus 1. Again, that means checking that the left hand side equals the right hand side of the equal to sign. When you finally see that step 3 holds true, then you can say that that formula or that theorem holds true for every natural number n. We'll see how it works in action as we go through some examples. Example 1. The example says prove that the sum of the cube of n natural numbers equals this statement here, which is n bracket n plus 1 all over 2 all squared. Now, what's our first step? Step 1 says we have to check whether the statement is true when n equals 1. So on the left hand side, when n equals 1, it means that we can just get rid of the rest of this, right? And we'll just have 1 power 3. On the right hand side though, what we'll do is we'll substitute, okay, let me just write it here, n equals 1. On the right hand side, what we'll do is we'll substitute n for 1. So anywhere we see n, we'll change it to 1, and then we'll see what it gives us at the end of the day. So let's do that. We have 1 plus 1 over 2 all squared, which is 1 times 2, 1 plus 1 is 2, all over 2 all squared, which is 2 will cancel 2 and we have 1 squared. On this side you have 1 power 3, don't forget. And 1 power 3 is 1, 1 power 2 is also 1. So step 1 is complete because the statement holds true for n equals 1. Now, step 2 says that we have to assume that it is true for n equals k, right? So we'll write it out again. So for n equals k, it means that n will be equal to k, right? So we have 1 power 3 plus 2 power 3 plus 3 power 3 plus all the way to k power 3. And on the other side, what we'll have is k bracket k plus 1 all over 2 everything squared. So our assumption is that this is correct. So let's try to simplify this a little bit. What we will have is k squared k plus 1 squared over 4. Step 3 says that we need to now check if the statement holds true for n equals k plus 1. So if we write out everything again, we have 1 power 3 plus 2 power 3 plus 3 power 3 plus k power 3 plus k plus 1 power 3. And on the right hand side, we will have, remember, anywhere we have n, we will exchange it with k plus 1 now, right? That's what we are looking at. It's right here. So we will now have k plus 1. Let me put it in the bracket for easy identification. And then we'll have another k plus 1, which is the n, plus 1 all over 2 and everything squared. Now, what I want us to see is that this part here is the same as this part here. So based on our assumption in step 2 that this is true, we can replace this entire portion with this. So we replace this entire portion, which is this one here. We replace it with this guy right here. So I'm going to say k square k plus 1 squared over 4 plus k plus 1 cubed equals the whole thing on this side. I'm going to simplify it a little bit. That's k plus 1, and then this is k plus 2 all over 2 all squared. Now, don't be dismayed. I know it looks like we're looking at a lot of k's and things are just expanding and expanding, but don't be dismayed. We'll keep on going, and hopefully, since we've been following things step by step, we will arrive at our solution. So let's copy everything out, okay? You have k square, you have k plus 1 square over 4. I don't want this to be k plus 1 power 3. I want to see if there's a way I can simplify this. So what I'm going to do is I'm going to say plus k plus 1 and then k plus 1 power 2. Recall, k plus 1 times k plus 1 power 2 is the same thing as k plus 1 power 3. Okay? And then on the right hand side, we're going to expand it, removing the power again, just like we did the last time in step 2. So what we'll have is k plus 1 squared. Then we'll have k plus 2 squared over 4, right? Please, I hope you understand that 2 power 2 is 4. That's why I have the 4 there. So this expression, if we notice, there's k plus 1 squared. In this expression, we have k plus 1 squared. And on this other side, we also have k plus 1 squared. We can see the like terms forming. So what we're going to do is on the left hand side, we will factorize k plus 1 squared. So we have k plus 1 squared. Okay, so what will be left after we factorize k plus 1 squared? We will have k squared over 4, and then we will have k plus 1. And on the other side, which is the right hand side, We factorize our k plus 1 squared. We then have k plus 2 squared over. Now we can cancel both of them out. Then we work with what we have left. On the left hand side, we will make 4 the denominator. We will have k squared here plus 4k plus 4. And on the right hand side, we still have 4 as the denominator. If we open this bracket, which is k plus 2 bracket k plus 2, for want of space, I'm just going to do it here. We'll have k squared plus 4k plus 4 all over 4. If you can see, the left hand side is equal to the right, which means that we have proven it and the theorem holds. Congratulations for making it up to this point. We'll look at the second example and then I'll give you one to try yourself.